Hi, Mr. Bouchard here, and I'm here to talk to you about density change and equilibrium. This is topic 1 of Earth Science, and these topics will be used throughout the year. So this introduction topic, again, we'll revisit these terms throughout the year over and over again. All right, so first, I usually start out with this experiment. I'll do this in another video, but this is clearly a density experiment, and it definitely it's an interesting one, so I will do this and you guys can check that out. All right, now density of objects. So most objects are going to be most dense as solid materials. You guys know this from, you throw a rock in water, it sinks. Okay, so more dense things tend to sink. Most objects are least dense as gases, that's why gases float above the Earth's surface. Objects that are less dense will tend to rise. Objects that are more dense will tend to sink. And the way to remember that is dense is down. So more dense materials will sink. So the reason why ice floats, ice is less dense than water. And you're going to say, well, most objects are most dense as solids. Well, water is a little weird in that way. Right? It doesn't follow that rule. So we'll get to that in a little bit. Warm water rises because it is less dense. Cold water sinks because it is more dense. Same thing is true for air. So the hot air balloon's a great example of this. So we heat up the air in the balloon to make it rise. So they pull that burner cord and it heats up the air in a balloon, causes it to expand out and becomes less dense, so it rises. And the warm air will rise. And then once it cools down, the air will actually begin to become more dense, and then it will sink back down to the ground. Okay, there's math along with density, and you need to know the formula. It's on the front of the reference table, at least so you should understand it. Density equals mass divided by volume. And mass is the amount of matter in an object. Volume is the amount of space the object occupies. Okay, so how close the particles of matter are in the amount of space is basically density. All right, so that's what we're looking at here. Now, size and shape do not affect density. So when you have a material like aluminum, okay, aluminum will have a unique density. It's actually 2.7 grams per centimeter cubed. So no matter how many times I cut it, shape it, make it large, make it small, no matter what, even if it's a cube, a cylinder, a sphere, it's going to have the same density. Right, because the ratio of mass to volume is going to be the same always. Also to know, you're not just going to have to calculate density. Sometimes you have to find volume and mass. So I'm going to show you a quick cheater method on the smartboard. So I'm going to go over to there and draw it for you. Okay, so just a little cheater method for this. So density is mass over volume. So I draw a little triangle like this. D goes on the bottom, M on top, and V on the right. Okay, and you put a multiplication symbol between the D and the V. All right, so the formula that you get from this, D equals M divided by V. That's the one we know, mass divided by volume. And cover up volume, and you're left with mass divided by density. And then also mass equals density times volume. Okay, so those are our three formulas, and that's how we can use it to find the other quantities if we need to. Okay. Now, density also can be thought of with objects such as this. All right, this is an iceberg. So this is a very large object, but it's still able to float. Why is it able to float? Well, just like we learned, it is less dense than water. So either way, doesn't matter how big it is, it will float in water. And you can see why the Titanic sank, hitting into one of these. 7/10 of the iceberg are actually underwater. 3/10 is out of the water. So it is buoyant, but most of it's still under the water. Okay, so that's what the danger of an iceberg is to a boat. Okay, so water I said was weird. And what makes it so weird? Well, it's most dense in its liquid phase at around 4 degrees Celsius. That's a rounded number. It's actually exactly 3.98 degrees Celsius, which is on the front of your reference table. All right, you can check out that next time when you get those. Less dense in the solid phase at 0 degrees Celsius and as a gas at 100 degrees Celsius. So that's not usual. Most things in their solid phase are going to be more dense. Gas will still be less dense. All right, so its density graph also looks slightly differently, and we'll be exploring that in other worksheets. It also floats in water when it is a solid, and again, that's what makes it very unusual. Okay, density has the ability to change. If you heat something up, it causes it to expand, and this will cause the density to decrease. All right, so you guys know this. Hot air balloon works this way. All right, so you pull the burner cord, heats up the air in the balloon, and the balloon expands. But when it expands, it's able to rise because it's less dense. And then the reverse is true. When it begins to cool down, the air contracts back out, and it begins to sink back down to the ground. Okay, now you don't want to do it too fast, because if the air quickly goes out of the balloon, it will sink very quickly. Okay, so that's why they do little burns coming back down to the ground. Okay, increasing pressure also will make matter closer together. So using the balloon once again, you can do this. Not just the air cooling down inside the balloon, but also the air on the outside of the balloon is pushing on the outside of the balloon. Okay, forcing some air out also. Okay, so increasing pressure will make the matter closer together and make it more dense once again and cause its density to increase. Diamonds actually are made from the same material that's in your pencil, graphite. So carbon, actually I should say carbon. Carbon actually, when heat and pressure are applied to it at a very high temperature, it basically turns into diamonds, right? It recrystallizes, right? So density increases there, and diamonds are much harder than your pencil graphite. So you guys know that. All right, what does this picture say? Well, this picture is a time-lapse picture of a tree. This is actually a European copper beech, which I have one actually in the front of my house. Very large tree. Shows the seasonal change very well though. Okay, so you notice up here in the top part of the picture, the green, that's summertime. The orangey red is fall. And then the twigs is obviously winter, and then spring. So basically this is saying that this tree undergoes changes. Okay, so these changes sometimes can be predictable, sometimes not so much, but either way, changes happen in science, and we're going to be looking at those. So change are when the properties or part of the environment have been altered in some way. Sometimes they're altered permanently. Sometimes they will return to their original state. All right, so cyclic change or cyclic change is something that changes but goes back to its original state that it was in. So that's predictable change. I think of the recycling symbol when I think of that. So a cyclic change is predictable. On a graph, it would be predictable. So we'll look at that in a little bit. Okay, how do we measure change? Well, there's a formula. Its rate of change equals change in field value divided by time. Change in field value is any measurable science quantity, and then time can be any unit of time depending on how long the experiment is going. Minutes, seconds, hours, days, all right, depending on the measurement. Okay, so I have a little example here mathematically, which I'm going to do up on the smartboard. Okay, so between 2:10 and 2:13 one day, the temperature change was 10 degrees Celsius. What is the rate of change? Okay, so what we're going to do on this question, we're going to first subtract the temperature change, which in this case they already did it for you. So we're just going to put 10 degrees Celsius on top. On the bottom, it's 2:10 minus 2:13, so 13 minus 10, which gives you 3 minutes. So your rate of change is going to be equal to 10 divided by 3. So 10 divided by 3 gives you 3.3 repeating. In this class, we're just going to round it to the nearest tenth typically. So it's going to be 3.3. And then the units are what's on top, which is degrees Celsius, divided by what's on bottom, which is minutes. So 3.3 degrees Celsius per minute is the final answer. Okay. All right. Now, also with change, what temperature is it like in this sort of environment? Well, you guys know this is a tropical climate, right? You always think of that when you see a palm tree, a warm climate. Why is it like that? Well, it's in something called dynamic equilibrium. All right, there is heat coming in each day. However, there is heat escaping each day. But in an area like that, it's pretty equal every day. All right, so you're not getting more heat typically throughout the year. It just stays the same throughout the whole year. So it's in dynamic equilibrium. It's a change that happens equally. Dynamic means change, equilibrium means equally. Okay, now graphs are also going to be an important part of this class. So direct relationship are graphs that slope upward. Okay, and indirect or inverse are the ones that slope downward. So when we talk about variables, I'm going to draw some stuff on this. If you put x and y on this, okay, if you, in a direct relationship, if you increase x, if you also increase y. Okay, and you do the reverse also. If you decrease x, you decrease y. So x and y do the same thing together. An indirect or inverse relationship, as once again x increases, y decreases, or x decreases and y will increase. So x and y are doing the opposite thing. That's why it's an inverse or indirect relationship. Okay, the next graphical thing I want to talk about with you guys is cyclic changes. All right, so a cyclic change is something that happens repeating. Okay, so what does that look like? That's a graph that looks like this. It returns to its regular state, it's predictable, and we can see it happening over and over again. Another one that might be seen, you've probably seen this before, heartbeat monitor, right? It's still predictable. The peaks might not be exactly the same. However, it's a predictable change. It's still a cyclic change. All right, and then the last thing I want to show you is an equilibrium graph. Move myself out of the way here. All right, equilibrium means that the graph is kind of not changing anymore. So you could have one situation where as x increases, x will always change, right? Because you're changing x in the experiment. Y will stay the same. Okay, and that's what that graph says. As x increases, y stays the same. Also, you can have a change that's happening, and then it will level off. When it finally levels off, that's when equilibrium has been reached. All right, so that's where it reached its equilibrium point. Okay, the last things I want to discuss are just quick definitions. So other things in earth science that are important: natural hazards, which are any non-human related object or process that has a possibility of causing loss of life. So earthquakes, volcanoes, things like that. So pretty much any natural disaster is a natural hazard, right? Tsunamis, so any natural disaster you can think of. Forest fires. Okay, interface. It's a boundary between regions of different properties. So an example in this room, you could think of the windows as an interface to the outside. It's blocking air from coming in and also preventing air from leaving. So that makes it an interface. And that makes the inside different than the outside. Okay. Also, natural resources. Okay, we have resources in the environment, which we harvest, and these materials and energy are used to make products pretty much, or even fuel some of the stuff we use in life. Okay, so either way, we need that material to be able to make products that we use on a regular basis. And lastly, pollution, concentration of any substance that reaches a level that affects the environment. Okay, so in other words, anything that causes harm to the environment. It could be water pollution, it could be air pollution. So these are things that happen to the environment, and we're the main cause of that. All right, thank you guys for tuning in, and I'll catch you next time.